simple harmonic motion. First, let's try to understand what we mean by a simple harmonic motion. Let's consider a spring and a mass attached to the spring and placed on a frictionless surface. And then we pull the block to the right and release it. So we can see the block starts oscillating back and forth. To understand the motion of the block, we can consider the forces. There is one force, which is the spring force, acting to the left, and if the displacement of the spring is x, we can say the spring force is equal to negative kx. This is from Hooke's law. But also we know that the spring force is equal to mass of the block times the acceleration. So mass times the acceleration equals to negative kx. That means the acceleration equals to negative k over n times x, or we can, in general, we can say acceleration equals negative times some constant squared times x. Omega squared is a constant, and we can equate that omega squared to k over m. By studying these motions, we understand that this omega is the angular frequency. So the angular frequency of this oscillator is square root of k over m. But anyway, in general, for any simple harmonic motion, acceleration is given by negative times some constant square times x. So if the acceleration of a motion satisfies a equals negative omega squared x, that motion is called simple harmonic motion. We in fact don't need to do that, so let's delete that. Okay, so that motion is called a simple harmonic motion. So that means if the acceleration of the motion satisfies a equals to negative omega square x, that motion is called a simple harmonic motion. So a displacement of such a motion, a displacement of a simple harmonic oscillator, can be given by this equation. X equals a times cosine omega t plus phi. X is the displacement, a is called the amplitude, and omega is the angular frequency, and phi is called the phase constant. T is time, and the amplitude is the maximum displacement of the oscillator. So the x max equals to a. Omega is the angular frequency or the angular velocity, but we call omega is the angular frequency. It's the same value that we call the angular speed, and phi is a constant, and it represents the initial position of the motion when t equals to 0. The velocity and the acceleration given by these two equations, v equals to negative a omega sine omega t plus phi, and a equals to negative a omega squared cosine omega t plus phi. The maximum value of the velocity is given by a times omega. The maximum value of the acceleration is given by a times omega squared. Now let's go over an example. The displacement of a simple harmonic oscillator is given by x equals to 24 cosine 6 pi t plus pi over 3 meters. A. Find the amplitude and the angular frequency of the motion. B. What is the phase constant? C. Find the displacement when t equals to 3 pi seconds. D. What are the maximum speed and the maximum acceleration of the motion? So the first question is to find the amplitude and the angular frequency. The amplitude, this is the equation. If we compare this with the equation of the displacement, we can identify that this 24 must be the acceleration. So the we can by comparing this equation with the equation for the displacement, we can identify that the amplitude is 24. So amplitude is 24 meters, and then 6 pi is the angular frequency, and also the phase factor is this constant, which is pi over 3. To find the displacement at t equals to 3 pi, we plug 3 pi here, so it becomes 24 cosine 6 pi times 3 pi plus pi over 3. So 25 cosine 18 pi squared plus pi over 3. So it's cosine of 56.85, and this value is in radians, so you must use the radian mode to find this value. So 24 cosine 56.85 equals to 22.7 meters. The last question is to find the maximum velocity and the maximum acceleration. Maximum velocity is a times omega, so that's 24 times 6 pi, 452.16 meters per second, and the maximum acceleration is a times omega squared, and that becomes 8518.7 meters per second squared. Example 2. The acceleration of a simple harmonic motion is given by a equals negative 16 cosine 6.28 meters per second square. Find the amplitude and the angular frequency of the motion. So in the same way, we compare the parameters. For the equation for the acceleration, we know that this value is equal to a times omega squared, and this is omega. By comparing that, 16 equals to a omega squared and omega equals 6.28 radians per second. So a is 16 over omega squared, 16 divided by 6.28 squared, so that's 0.41 meters. The spring mass system. The spring mass system consists of a spring and a mass attached to it. It could be an oscillation in the horizontal direction or an oscillation in the vertical direction. For such a system, we can say that the acceleration is negative k over m times x. This k over m is omega squared, so omega is equal to the square root of k over m. So for a spring mass system, the angular frequency is given by square root of k over m. K is the spring constant and m is the mass. And the important thing about the spring mass system is that the angular frequency is independent of the acceleration due to gravity. The second example is the simple pendulum. A simple pendulum is a pendulum which consists of a point mass and also oscillates through small angles. Then we can show that the angular speed is given by square root of g over L. L is the length of the string and g is the acceleration due to gravity. For this pendulum, the angular frequency depends on the acceleration due to gravity. So the third example is the physical pendulum. In this situation, the only difference is the object is not a point particle but it's a rigid body, but still this object oscillating through small angles. then we can show that the angular frequency of this oscillation is given by square root of mgd divided by I. D is the distance from oscillating axis to the central mass, and I is the inertia of the object. Example 3. Spring mass system consists of a light spring of spring constant 80 newtons per meter and a 2 kilogram mass. Find the angular frequency and the frequency of the oscillations. Question A. Find the angular frequency and the frequency of the oscillations. Question B. What is the period? C. The amplitude is 15 centimeters and its displacement at t equals 0 is 8 centimeters. Find its displacement at t equals 3 seconds. So we know that for a spring mass system, the angular frequency is given by square root of k over m. So that's square root of 80 over 2 square root of 40, so that's equals 6.3 radians per second. And the frequency is given by omega over 2 pi. So omega is 6.3. We already found that, so over 2 pi. So that's approximately 1 hertz. Then we need to find the period. Period is 2 pi over omega, also 1 over f, so 1 over 1, so that's 1 second. To answer part C, we need to find the amplitude and the phase factor. Question C is asking us to find the displacement at t equals 3 seconds. The amplitude is 15 centimeters. So we have the amplitude, but we still don't know this phi. So to find phi, we can use the information given in the question. It says at t equals 0, the displacement is 8. So if we use that, we can say 8 equals to 15 cosine phi. So that means cosine phi equals to 8 over 15. Phi equals 57.8 degrees, approximately 1 radian. So x equals 15 cosine 6.3 t plus 1 centimeters is the equation for the displacement. Now we know t equals 3 seconds. So if we plug 3 here, we can find the displacement at 3 seconds. 15 cosine 6.3 times 3 plus 1. So that's equal to 15 cosine 19.9, that's 7.32 centimeters. Example 4. A student wants to make a simple pendulum that oscillates with period 1 second. Find the required length of the pendulum. For a simple pendulum, omega is given by square root of g over L. But the period equals to 2 pi over omega, so that's 2 pi times square root of L over g. G is 9.8, t equals to 1, so 1 equals to 2 pi square root of L over 9.8. So by squaring both sides, we get 1 equals to 4 pi squared over 9.8 times L. Solving the equation for L, we get L equals to 9.8 over 4 pi squared.